So this is the last talk for today.
It is.
And it is. So as being a German myself, the last thing I want to do is keeping us all from going to the German beer garden. So bear with me. I try to keep things brief. But anyway, I have to tell you something. So my name is Nitzold, and I'm from National Instruments in Dresden, Germany, actually, where I'm part of a small research team that is basically drawn to communications research for 5G and beyond communication systems. And what we do is that we basically participate in EU-funded or otherly funded research projects to do research. Yes, exactly. So this is work that I did together with my colleagues Clemens, Felber, and Vincent, Kotzsch. And I wanted to talk a little bit about how to prototype LTE and Wi-Fi interworking technologies, and especially doing that on an SDR platform. So the question is, what does motivate that work? And I think we have heard it before in some of the other talks already, that with future and upcoming communication systems like 5G and so on, there are lots of different applications that pop up, like whatever, virtual reality and high throughput video streaming or whatever. So there is quite a big demand for higher throughput, but on the other hand also for lower latency, so those different KPIs or metrics that need to be optimized. And you can do two things for that. The one thing is that you can optimize the radio access technology itself. That is done, for example, in LTE and Wi-Fi itself. But what is a currently ongoing and interesting research communications paradigm is actually to combine different radio access technologies and do interworking between those different technologies. And this is a little bit motivated by an end-to-end point of view, that an application doesn't care about the underlying communication technology as long as those KPIs like throughput and latency are satisfied. So it's kind of a transparent end-to-end point of view that we have here in mind. And this is what we wanted to study in conjunction with a research project that we did in Germany. So the question for us was how to actually study those interworking technologies. You can see it here on the bottom, actually, just to conclude on that. You have a transmission or a communication system here where you have a server or an application, and then you have a network in between, and then you have the connection to a access point for Wi-Fi and to an E node B for LTE, and they both are connected to something that we would call a multi-RUT user equipment or something, which is kind of your normal mobile phone that has a Wi-Fi chip and it also has an LTE modem inside. So, and your application would actually talk to that. So how can you actually research these interworking technologies or these two radio access technologies together? And so we had a look into what is actually available in the open source world and also beyond that. And it turns out that there are quite a few solutions there. So those are solutions that are actually not open source, but commercial. Or I think SRS has something also available open source, I think. And on the bottom, you see different options for open source implementations of different radio access technologies. And basically all of them have different functionality. For example, Open Air Interface is something that incorporates LTE transmission and also has a path for 5G, while Linux 802 Mac is something that only incorporates Wi-Fi transmission. And there is also NS3. So after looking through all those different simulators or technologies or software stacks, we actually came up with the idea of using NS3, and it had certain reasons. The first thing is it's open source, so that was quite intriguing for us to use that. And it actually allows for completely simulating IP networks within this network simulator. So this was quite nice to have an overall system that can simulate a complete communication system. But beyond that, it also has support for different radio access technologies, and we were especially interested in LTE and Wi-Fi. So NS3 is actually capable of doing simulations for that, so that's why we actually were drawn to this and we tried to use that. So the question for us is Network Simulator 3, NS3, is purely for simulations there. So it's from the computer science community, they use it completely for simulations. So for us the question was, how can we get rid of the simulated channel and integrate real SDRs to have the chance to do real over-the-air transmission. Therefore, we have to have a little bit of a look into, I guess you're all familiar with that, the OSI model of transmission. So the different layers of this transmission model that kind of model different functionality within the communication system. And if we look onto a specific LTE stack implementation of this OSI model, we can actually see the different layers. For example, we have the PHY layer on top. I guess you are aware of this, how this thing works. We have the physical layer who does specific functionality, and then we have the other layers on top of that. And basically giving different functionality for the communication system. And then on top, we have the user plane and the control plane, which actually does the IP connection to some application in the end. So for us, we had we were looking into some physical layer implementation, and it turns out that National Instruments itself has something available for the physical layer, which is the application framework that has an LTE and a Wi-Fi implementation. Could also be something else. For example, what I would be really interested in to see is how we can especially use GNU Radio for simple physical layer implementations, and especially also RF NOC for that. That would be interesting. But in that context, we were missing the upper layers. So the question was, how do we use the upper layers? And that's why we actually used NS3 in the end. So below that, we have specific physical layer and especially FPGA implementation here. And on top, we decided to use NS3, which is Linux-based C++ implementation of the upper layers. So this is the idea behind that. And so we needed to somehow connect the upper layers of NS3 with our physical layer implementation and with the SDRs themselves. So we needed to have some point where we connect those two worlds, so to say. And this is where we started to think about the concept of having a generalized L1, L2 API. So an API that actually connects the lower layer, the physical layer, to the upper layers. And this is what this work is all about an API that connects that generalized or a generalized solution to connecting a physical and MAC layer and the paradigms behind that. As I just said, we just looked onto a cellular type of thing, and what with this API concept is actually possible is that we have the option to kind of, if we have a generalized API concept, we can interchange things that we want to do. So we have several different options. For example, we can exchange the physical layer, and instead of LTE, we could use possibly a 5G NR or a 5G or whatever, a 6G layer, put beneath that and make it compliant to the API, and same thing on top. So if, for example, someone wants to do something in LabVIEW, he can do a LabVIEW-based Mac implementation or use some other third-party or open source protocol, L2, or even a complete protocol stack, as we did in this example here with NS3. And there could also be the option to include other APIs, like between layer 2 and layer 3, and then you can have another implementation on top, which you just plug together. Exactly. So this is the cellular part, but as I said, we are also looking into Wi-Fi. So this is why on the right side, we have also the Wi-Fi path. And we thought about how would we do this implementation of an API. We came up with the idea to make things easy and align concepts, so such that you have one generalized architecture and you can kind of use that and reuse that. And it was a basic goal for us to use concepts that we have here, also in here, in terms of concepts, mechanisms, and also the general message structure that this API is using. So what advantages or what potential does such an API system actually have? So at first, you have the same ease of use. So no matter if you use LTE API or if you use an Wi-Fi API, it's the similar matters, similar concepts that you use, so it's really easy to use. It's relatively flexible in terms of configuring a lower layer, a physical layer, to actually incorporate this into end-to-end simulations with NS3 and so on. Another thing that is really important is with having a generalized API concept and an implementation of that, you are really fast in adopting this to new implementations. For example, what we're currently doing is that we are looking a little bit into a 5G path, and it's actually pretty easy to just take what we already had in the implementation and the specification for an API and just put that onto a 5G physical layer implementation with slight adaptations, and then we could use that. What it also helps is in terms of system abstraction, because if you use an API, especially for a pretty sophisticated physical layer implementation, you can get rid of all those detail of the physical layer and just use it with a defined interface of this API to the lower layer. Exactly. And as I said before, the reuse, this is somehow, as I said before, it's really nice that you can just use the API and also the implementation and adapt this to other physical layer implementations. Okay, so let's have a look on how this API actually works. So the general principle of this API is that it's based on 3 message types that we actually have defined here. And they are exchanged between the file layer and the MAC layer. So the first thing is that MAC layer could send some kind of request to the physical layer, and then we have a possible confirm of that request. So if MAC layer is sending a request, it could be confirmed by the file layer that this request has been processed. And then the physical layer could also send some indication up to the MAC layer transporting some information. So an example is here on the right side. You have a TX request for the data channel. That means so you have some control data, and the MAC layer is actually sending such a TX request with data that needs to be sent over the channel down to the physical layer, and with that some control information, which would, for example, include the modulation encoding scheme, a resource block allocation, and things like that. And of course, it needs to transport the payload to the physical layer that the physical layer can basically process it and send it over the air. Exactly, so this is the basic paradigm, the basic messages, and there are specific messages that are drawn then either to Wi-Fi or to LTE, depending on the physical layer that you're actually using. This is a sequence chart that should give you a little bit of an insight in how the structure and the functionality for especially LTE works. So the interesting thing about this is that LTE itself runs it has an inherent tick of 1 millisecond, which is a subframe that is constantly running, and the physical layer is actually running in that time scale. So in that sense, the eNode B, or the base station physical layer, is the timing master, and one message that is going to be sent every millisecond is a so-called phi timing indication that indicates to the upper layers the timing grid, how the physical layer works. And with that timing indication, the MAC layer actually is going to send requests to the physical layer of transporting data. And this could be, for example, here a downlinked TX config request that actually requests to send some data over the air, and it has some actually those are 2 sub-messages of such a request. The one is the config request message that actually configures the physical layer to a certain state, and then we have a downlinked TX payload request, which is actually conveying the data that needs to be sent. And in the same subframe, we don't only want to send data, but we probably also want to get data from the physical layer because there was something sent in the uplink. So that's why actually the physical layer here of the eNode B is actually sending a uplink shared channel RX indication. So that means it indicates to the higher layer that data is there, and it actually sends this data upwards such that the MAC layer can process that. And then everything of this has to happen within 1 millisecond, because after 1 millisecond, the physical layer is actually again sending a timing indication for the next millisecond, when things going to be processed newly for the next subframe, so to say. And basically the same thing happens on the UE side too. Exactly, and the important thing here is that the FPGA on the eNode B here, or the physical layer, is the master clock, and everything else has to cope with that. And this is actually also a problem that we have foreseen, and we are currently heavily optimizing for that, because the physical layer, and especially this FPGA implementation, it runs rock stable in 1 millisecond tick, and if NS3, which we had here on the side for the upper layers, if it doesn't get everything processed within 1 millisecond, we get problems because we're running out of sync, and that's why we actually need to have also the upper layers kind of run relatively fast. And they're also ideally would run on a real-time system such that you can really guarantee that everything is being processed within the 1 millisecond that we have here. Okay, so how is this actually implemented? So this is one thing that I want to also show because this is the interesting thing about this API and actually the difference between the API specification and the API implementation. So what you would have in your system is that you have one L1, right? The physical layer, in our case this is LTE, and we have the L2 MAC layer or the upper layers, and we need to make them work together with the API. So what you need for that is actually you need some message handlers and message generators that are capable of talking to your actual physical layer implementation. So they talk in the interface that your physical layer implementation would request or would use, right? And so this is an implementation-specific interface. It could be different on C++, could be different on FPGA or whatever. And the same happens to be on the L2 side, so on the upper sides. So there's also a specific, or implementation-specific interface. For example, in our case, on this side we have an FPGA implementation in C++. On the upper side, it could, for example, also be a LabVIEW implementation or whatever kind of implementation, something in Python. So you need to have some message generators and some message handlers that are written in your language of your solution and that need to talk to your L2 or L1 implementation. But those message generators and message handlers are actually the ones that translate your implementation into the API's basic specification. And this is where this is actually the other interface. So this is the common message interface that we implemented here, such that these two different implementations can actually talk to each other. And so now you have translated basically the interface from your implementation towards the API interface. And what is left to do is kind of transmitting those messages, those API messages, somehow to the other part. And there you're also relatively free to go. So the only thing you need is to have read and writes for a specific transport medium that you want to use. And I just said you are relatively free to use whatever you like, although there are specific constraints depending on what kind of time constraints you have in your implementation. So you could, for example, send those messages over UDP via Ethernet, for example, if you want to plug an L1 over Ethernet to some network simulator or something like that. But depending on your implementation, you could also use just memory pointers or direct access or a C API that you use for that. Or even if you're using that directly on an FPGA or something, you can use FIFOs for that, things like that. Exactly. So this is something really which is up to you. And for example, for LTE and for Wi-Fi, we use different transport mechanisms because in Wi-Fi, we had an implementation that actually has the time-constrained Wi-Fi processing in the FPGA. So we were relatively relaxed in terms of timing constraints. So that's why we could actually use UDP for the transmission of those API messages. For LTE, however, we needed to really go in this 1 millisecond tick, and that's why we needed something that is way less jitter-prone, I would say, than UDP actually is. So we did some tests, and it didn't turn out well. So we actually went for transmission via Linux pipes to actually get those messages from L2 to our L1 implementation. So this is something when one really needs to figure out based on the specific implementation what is sufficient for the use. Okay, and we did actually do an implementation for that. And for that we used some specific USRP hardware. This is the USRP 2974. Which is a specific USRP that actually includes an Intel i7 CPU. And this was a perfect fit for our implementation because we needed something where we could run those message handlers on. And we could run actually a Linux distribution on this Intel CPU. So we were actually capable of, additionally to the message handlers, we could also run the complete NS3 on top of that. So this all runs in that box. And as we have LTE running and Wi-Fi running for doing this interworking research, we have one internal FPGA in this USRP, which actually runs an FPGA implementation of LTE. And we wanted to use Wi-Fi too, so this actually has the opportunity to attach another USRP with a PCI expansion board. So we have a second USRP which just has an FPGA, and this runs the 802.11 implementation. And yeah, basically all of this fits just in this one box, and this is actually quite nice because we are using this also in the research project in conjunction with test beds in Germany, especially in Dresden, where we have those USRPs running, and this is quite neat and easy to, and portable, I would say, to have wander those things around and do different tests. Exactly, so with this setup, we actually were capable of having this complete end-to-end system running just on this one machine. Exactly. We also did some tests regarding, or let's say some simple tests to measure actually the end-to-end throughput. So what we did was actually that we had a application for data transmission from a server point of view, and we actually sent it over the complete system towards our so-called multi-RUT user equipment. And yeah, it's probably a little bit hard to see, but what we did is we checked different packet sizes, and we decreased the packet interval, which would result in higher throughputs. And you can actually see that we get higher throughputs. So the theoretical limit of LTE is actually 75 megabits per second. And with this implementation, we get, I would say, relatively close. So we are a little bit below 70 megabits. And this is quite a strength of this segmentation, of having an FPGA implementation for that and having the end-to-end stacks on top, that you can do end-to-end measurements or end-to-end experiments over the air with those throughputs. Exactly. So I think this is it already. I don't know what's the time. Okay. So what did we do? We have this generalized API specification to connect physical and MAC layers of different RUTs. So we did this for LTE and for Wi-Fi. And with this, and in conjunction with NS3 as the network simulator on top, we were actually capable of doing interworking research. And there are actually universities in Europe, especially in Spain, that are working on specifically those interworking technologies between LTE and Wi-Fi, and they actually use our platform in conjunction with this research project called ORCA, where they actually also helped us implementing these things, and they're using that in a testbed of the Technical University of Dresden here in Germany. Exactly. And one last thing here is that this implementation that we did for this L1, L2 API, we actually made this available on GitHub, and we, as good as possible, we tried to maintain this and feed new things in and new features and so on. For example, we recently had actually it was another university from Spain. They seem to be drawn to that kind of network simulator. They did another implementation of interworking technologies between LTE and LTE, so-called dual connectivity, and they implemented this in NS3, such that it can now be used actually in the test beds. Exactly. So this is free to use here. So check out GitHub, the NI NS3 application example. Other than that, what we will do next is, we basically want to maintain what we did and also kind of get in new things, new features into this network simulator. Exactly. What we also want to do is to look a little bit beside NS3 and also look into OpenAir interface. I think we mentioned that beforehand, that there was an OpenAir interface demo at the NI booth, right? So this is what we are currently also looking into, or start looking into. We see how we can exploit this API interface also for OpenAir interface. And last but not least, we are currently working together with Technical University of Dresden, because they have a very specific physical layer implementation of what they think could be 5 or 6G, I would say. This is a specific modulation scheme called GFDM, and they have a physical layer FPGA implementation for that, and we are working together with them to actually get the API on top of that, such that we can plug everything together to NS3, and we have actually 3 different radio access technologies in NS3, which researchers can use for doing research. I think that's it. Thanks.
All right. Perfect on time, German punctuality. So that means we can ask a few questions, yeah?
Have you considered using like an RF channel emulator in addition to this, like connected to the actual hardware to do additional things, like especially for satellite orbits, if we can emulate what the channel looks like and add that to the simulation so you can have the hardware there. Is that something that you've looked at or no?
Can you say it again? Why would you use
So
it
like
on-
adding like an RF channel emulator to this work. So you have your NS3 at the top layer talking to an actual physical device, and then that connected to an RF channel emulator that would emulate the environment that you're trying to look at.
So we haven't, although we had discussions with Technical University of Dresden, because they have done things before for their 5G GFDM physical layer. So you can do two things. Usually when we test this stuff, we do it cabled, because that's the easiest way, and you get a plain smooth AWGN channel. And other than that, if you have a license, especially for LTE, somewhere, and actually Technical University of Dresden, they have a test license to also run LTE, so you can just use plain antenna and also play with that. But actually RF channel emulators, which we put between the system, we haven't done yet, no. Thanks.
Are there any other questions? Actually, I have one. You mentioned a project from a Spanish university. I did not catch that. That's not on this slide, right? Or is it?
Well, it's actually in conjunction. So this ORCA research project is an European-funded research project where we have a consortium of like 7 partners. And the specific of this project is that the partners are working in that project together to do things. But we also have so-called open calls where we ask, or where we promote externally that partners could apply for those open calls to actually do research on the platform that we are offering in that project. And there are calls where actually partners from Spain actually wanted to implement specific things. So for example, this Wi-Fi LTE interworking, this was an offer which we had. We thought it would be nice to have that in the NS3 network simulator. And this university from Spain said, okay, I want to do that. I apply for this open call, and they won. So they got funding for, there was like 9 months to actually implement and test this, and we worked together and got that working. Yeah.
Okay, well that's very cool. So one final round of applause for all the speakers and for Walter.